Okay, in this video we're going to talk about some integration by substitution. And one of the things that's so important to think about when you're doing integrals is to always kind of go down a list of methods, in that you don't want to do the hardest method when an easier method would work. And one of the things to look for with substitution is look for a product or a quotient where if you made one of the functions u, the derivative would be the other function or some version multiplied by a constant of the other function. For example, and maybe I would like to do the gray box one here first. I've got a product here, x multiplied by e to the x squared, where if I made u equal to x squared, du would be 2x. Well, I've got an x dx. And sometimes it's nice to even rewrite the problem in a new order. And I don't know that we need to do this for very long, but sometimes, it's nice to just say, well, multiplication's commutative. I can swap the order here. If I made u x squared, then du would be 2x dx. I could divide both sides by 2, and now I could replace the x dx with a 1/2 du. So this integral would become e to the u multiplied by 1/2 du. And then I would take the 1/2 out front. I always bring a multiplier up front like that. And the antiderivative of e to the u is e to the u. So 1/2 e to the u plus a constant. And of course, the last thing we should do, I'm going to put my answer out here, is substitute back in. So I've got 1/2 e to the x squared plus a constant. Okay? Let's go back up to the first one. This one looks a little bit tricky. But if you think about this, if I made u equal to the denominator, u equals 2x squared minus 6x plus 1, then du, the derivative, would be 4x minus 6. Well, look at the numerator. It's 2x minus 3. If I factored a 2 out here, du is equal to 2 times 2x minus 3, like that. I could divide both sides by 2, and I could replace the 2x minus 3 dx with a 1/2 du. So this integral would become 1 over u multiplied by 1/2 du, like that. I could replace that whole thing. Now, sometimes it throws people to say, well, how did you just yank this whole thing out? Remember, 1/2 or 1 over u times 1/2 du, really you just take this whole thing and multiply it by the numerator. So that's why you can pull that down. You also could have yanked the 2x minus 3 down and had it be 1 over this times 2x minus 3 dx. But again, I would pull that 1/2 up front. The antiderivative of 1 over u is natural log. So I've got, I don't want to quite get out of the box yet. I've got 1/2 the natural log of u plus c. I'm going to put some absolute value signs around it, just paying attention to the fact that it does have some domain issues. And I put back in 2x squared minus 6x plus 1. And remember, we can't take the natural log of a negative, so that's why I put those around it. One of the trickiest looking ones here at the end, 1 over x natural log x, maybe would benefit from you thinking about it like it's 1 over x times 1 over natural log x. Of course, in multiplication, we just multiply across. And here you could make u equal to natural log. So du would be 1 over x dx. So again, I can replace this entire 1 over x dx with just a du. So this becomes the integral of 1 over u du, which is the natural log of u. Well, u is natural log of x, so it becomes the natural log of the natural log of x plus c. It's not natural log squared. It's not a multiplication. It's a composition. Now, I also want to talk about a slightly different kind of substitution, but one that's pretty valuable to recognize. Notice here we've got x times x plus 1 to the 10th. Now, this looks like a real prime example to use substitution, but unfortunately, if I made ux plus 1, du would be nothing, so it is thrown off by this x out front. But I certainly don't want to actually multiply this out 10 times. So we have a substitution with one extra step, and let me show you what I mean. If I make u equal to x plus 1, then du is equal to just dx. So where I'm at here is I've got this is u, and this is du. Okay? Now, unfortunately, that doesn't help me get rid of this thing in the front. But take a look. What if I took this first statement and I said, u is x plus 1, so then x is u minus 1. Now let me try and rewrite. So x is u minus 1. X plus 1 to the 10th, well, x plus 1 was u, so this just becomes u to the 10th du. Well, take a look at this. I can multiply u to the 10th in, and I end up with an integral of u to the 11th minus u to the 10th du. Well, the antiderivative is 1/12 u to the 12th minus 1/11th u to the 11th plus c. And then I just plug u back in. 1/12 x plus 1 to the 12th minus 1/11th x plus 1 to the 11th plus c. And that's the antiderivative. Okay. This works really well, as I said, for those times when u and something outside have the same power. Okay, it works really slick for that. So let's try this. We've got, on this one, u equal to x minus 2, so du is dx. And if u is equal to x minus 2, then of course x must be u plus 2. So let me rewrite. The integral would be u plus 2. Now, of course, the square root's the same as 1/2 power, so it becomes u to the 1/2 du. Well, multiply that u to the 1/2, and I have u to the 3/2 plus 2u to the 1/2 du. Antiderivative, let me come down here. I'd have 2/5 u to the 5/2 plus, I'd raise the power to 3/2 and multiply by 2/3, so I have 4/3, like that, plus c. Substituting back in, 2/5 x minus 2 to the 5/2 plus 4/3 x minus 2 to the 3/2 plus c, like that. Okay, let me start one more. If I make u equal to x squared plus 1, then du is 2x dx. Okay, now take a look at this. This is the first time this is going to happen. 1/2, like that. I've got to split this up into x squared times x. Okay? Because when I come down here and I say, well, if u is x squared plus 1, then x squared is u minus 1. So I should replace the x squared with u minus 1, the square root of x squared plus 1 with a u to the 1/2, and the x dx with a 1/2 du. Let me say that one more time, because this is very similar to the last one, so I'm not going to finish it, but it's worth talking about again. When I make u equal to x squared plus 1, du is 2x dx. Well, this is x cubed, which I could rewrite as x squared and x. So I've got the x dx right there. Well, then I replaced, or I rewrote, u as x squared plus 1, so then x squared was u minus 1. So I could replace this with u minus 1, this with u to the 1/2, and the x dx with a 1/2 du. And at this point, yank the 1/2 up front, and it looks almost exactly like the one above it. Okay, last problem looks something like this. Now, you have two strategies when you see something like this. The first would be to actually divide it, which, you know, if you said x minus 1 divided, or x divided by x minus 1, you do it that way, and that will work fine. But you do have a substitution strategy as well. We always have talked about making u the denominator. Okay? But what if I did this? And I could then rewrite this as u plus 1 over u du, which I could write as u over u plus 1 over u, which I could write as 1 plus 1 over u du. And now it's a very easy antiderivative. It's u plus the natural log of u plus c. Substituting back in, I have x minus 1 plus the natural log of x minus 1 plus c, like that. Because the tricky thing is always when the denominator is more complicated, because you can't split a denominator, but you can split a numerator. So using this technique allows you to rewrite it in an easier fashion, split the numerator up, simplify, and do the antiderivative.